morning, everyone. Kind of got a little list over here to try and help me remember to keep track. We're working on continuity still, section 2.5. We're going to be spending time looking at continuity questions that involve the piecewise functions. That's really a big chunk. Some continuity questions involving rational functions, mostly removable discontinuities in these cases, and a little baby application question right at the end. So this is what continuity looks like if you want to test it. It's by using limits. So the first one is a function is continuous at some number x equals a if the overall limit as x tends to a is the same thing as the value of the function. What that would look like is pretty nondescript. At that point there, it's a, and over here is f of a. So isn't continuous just another way of saying there's nothing wrong with the graph, right? It just is a smooth, it travels from one place to the other and nothing going on. In fact, where my finger is pointing right now is continuous, so is there's continuous, so is here is continuous, and everywhere else is continuous. So when you're thinking about what is continuity of a graph, I just think of it as just a normal curve with nothing weird going on. Nobody's going to get killed as you travel along the road. And then we have two other types of continuity. We have right continuous and left continuous. Also called continuous on the right, also called continuous on the left. Well, they look a little bit different. If you have, for the most part, these questions tend to be jump discontinuities. But if you have a shape like this, as you come in from the right-hand side, there's a dot. That's what right continuous looks like. You can imagine this is A, and the location of the dot is the value of f of a. So you can see it's stuck right at the end. That is right continuous. And then lastly, you can have left continuous, which would look like this. Only the left branch has the dot at the end of it. And this is where x equals a is, and this is the value of the function. So let's do questions involving piecewise functions and looking for places where the function might be left or right continuous in particular, right? And to be able to do that, I kind of need to do Desmos. So I'm getting that set up. I think I got it. Okay. Something's got a lot of windows open here, so if you just bear with me for a few moments. Come on, open up. Oh, it has opened up. I'm just looking at the wrong place. Right, I think I've got everything in place. Here goes. So first question I'm going to do, just to give you an example of how you're going to be using Desmos in these situations, is question 11. Let's see what that looks like. Okay, in question 11, we have a function that is x plus 5 when x is less than or equal to -1, and it's x 2 to the power of x, I should say, when x is greater than 1. Now in Desmos, if you want to make a piecewise function, you do a little curly bracket and you put in x less than or equal to 1. Then you do a colon and you don't type in y equals x plus 5. You just type in the x plus 5 part and then you finish the colon. That should do it. Go. Can you see it goes that way? And then the second part of the piecewise was 2 to the x, and that was for x greater than, oh, it's -1. Okay, I'll fix that right now. Colon, and it's going to be 2 to the power of x. Got to be careful with brackets. I'll use my mobile. Right. It's not this hard. It's just I'm trying to reach over to do something that I can hardly see the keys when I do that. There we go. And this fella here should be -1. Now, Desmos is really good at drawing piecewise functions. In fact, if we just zoom in on the part that matters, can you see at x equals -1, there is a jump discontinuity? Great. Now, what Desmos is not good at, and I'll zoom in right now, do you see there's no obvious, is that where the solid dot is, or this is? That's where you have to kind of use this. The straight line, that's this guy here, that's the one that gets the dot. Now, if you want to make a dot happen, you can do it. You can just plug in the point -1, 4 by going like this. Yeah. Do you see I've now gave it the nice solid dot? Right. If you look at that piecewise function, what is happening at x equals -1? Is it left continuous or is it right continuous? There's the clue where that little green dot is. Left continuous or right continuous?
Left continuous?
Correct. Now you see this red line is the left branch. This blue curve is the right branch. The guy that's got the dot is the left branch. That is left continuous. Good. Now, in the question that you can't see, I'll just read out. They give you a number of things that you have to explain why this given number happens to be left or right continuous. I've lost the thing that's disappeared on me. And they give you some questions to use that graph to answer. Is the value of the function at f of -1 undefined? No, f of -1 is defined. Is f of -1 and the limit, the overall limit, are finite but not equal? That's true. Well, actually the overall limit, I'll take that back, does not exist. It says, are the left and right limits finite but not equal? That's the one that is not true. And then the limit is it, overall limit does not exist, and then none of the above. Okay, I think that's too much to read out. I'm going to just return it to the question and show you. Right. Okay, you remember that guy? Because you're going to see 4 choices in a second. And then I'll try and answer that question, hopefully a little bit clearer. Here. Now, the guy that we had was this picture here. The second one. Here is the piecewise function. That e equals -1 basically just told us where to look. So the first question is, f of -1 is undefined. Well, the value of the function at -1 has a dot there, right? So that is is defined, so I'm not checking it. This one says f of -1 and the overall limit are finite. No, that's not true. This one says that these two limits exist but are not equal. That is true. The left limit is 4 and the right limit is whatever that number is. The next one says the overall limit doesn't exist. That is true. So that would be, I think, the choice that you would use in that question. You know, I wish I had 3 screens. There's too much stuff going on. Just makes it hard to keep track of them. Well, hopefully you got the gist of that question because it involved a picture. Let's bring that over here. I think I'll try the next one a different way. Maybe this will work better. Yeah, this is my little mobile keyboard because when I use my normal one, it's kind of way over here at the road. So let's make our next guy. Next piecewise function looks like this. So this would be an example of this would be question 16. It's 4x squared when x is less than -1. It's 4x when you use x between -1 and 1. And you use 4 over x for x greater than or equal to 1. Now, the equals parts here and here tell you where the solid dots are going to go. And then they have a whole list of questions all about that guy. Now, I could definitely put that into Desmos, but if I did it to Desmos, you wouldn't see the questions. So that's what my problem is. So I'm going to draw a little baby version of what that would look like. Okay, so here is x equals -1. And if you do 4x squared, you will get the number 4, you'll get a circle, and you'll get a guy curving like that. You pretend that that's what it looked like in Desmos. Okay. Then you get 4x starting at -1. So that would get you a guy down here. And then at 1, you get a guy up here. And the -1 guy gets a solid dot, and it's a straight line, and it goes to a circle. Can you see the solid dot is at the -1 side, and that's meant to say an open circle at the 1 side. And then that's meant to be 1 here. And then at 2 and 3 and everybody else, you do a curve. Now, 4 over x, actually, I'll put it as a different color. It overwrites that guy, and then it looks like that. So if you'd put this into Desmos, you'd see a curve like this with a hole, a solid dot straight line with a hole at the end, and then superimposed on top of it, a solid dot with a curve. Right, now that we've got that, here goes. The first question that they ask you is that guy. When you look at this picture, the value of the function at -1 is where that dot is, so it's -4. Now, if you wanted just to use the formula to ask that question, if you're asked to find the value of the function at -1, you look at which one of these has -1 in it, and it's this one. So that means you use the rule 4x. And so you would go 4 times -1 is -4. So that's how you could do it algebraically. The second question is they ask you for the value of f of 1. Now that happens to be there, and that's 4 as well, by coincidence. The third question that they asked is the limit as x tends to 1 minus of this function. 1 minus is a left limit. It means you're coming in close to 1, but from the left-hand side. All right, so here is x equals 1. And if you're coming in from the left-hand side, you get to there, which is 4. The next question is the limit as x tends to 1 plus. 1 plus is a right-hand limit. As you approach from this side, oh, you also end up being 4. Don't think they asked this question, but if they did, what would the overall limit as x tends to 1 be in this case? What's the overall limit as x tends to 1 in this question?
4.
It would be 4. Aren't the left and right limits coming together at the same point? Right? Doesn't that mean that this function is continuous at 1? Although they never asked that either. But if they did, yes, they are continuous at x equals 1. I'm kind of running short of room. I want to keep it all in this picture. What would be the limit as x tends to -1 minus? Right. A minus means a left limit. So you're coming in from the left branch, and the limit would be 4. If you do what is the limit of that guy, anything with a little plus means a right limit. You're coming in from the right-hand side. So as you come closer to -1 on the right-hand side, you get -4. As a left limit, as a right limit, does it have an overall limit at x equals -1? Does this thing have an overall limit as you approach -1 from both sides? No. Doesn't that mean that this is discontinuous at x equals -1? In fact, isn't it a jump discontinuity, if you wanted to give it a name? On the other hand, isn't this function continuous at x equals 1? So it's quite, for me visually, it's quite easy to tell. Discontinuity is, you get killed as you're traveling along the road, right? The graph is broken some way. Continuous, no gaps, no breaks. As you travel, you can go from one side to the other without any real issues. Now, so that's basically it, right? You've got a piecewise function, and then you're going to be asked lots of different questions about the value of the function at critical points, and then about things like, is it left continuous? Is it right continuous? And so on. Any questions about that? Because they are kind of a lot going on. Are we good? Okay. Example of question 19. You're having a piecewise function. It's made up of 3 bits. You use the rule x plus 3 when x is less than 0 but not equal to it. You use e to the x for values of x that are between 0 and 1, and you do use them. So that's where the dots, the solid dots, are going to go. And you use 2 minus x when x is greater than 1. I'll try and draw a sketch of this. This is what Desmos would look like. I'm not using Desmos. So here's 0. And if x is less than 0, over here is going to be the straight line x add 3. So put a little circle there, and off you go. That line's not there. Pretend that line's not there. It goes this way. That line's not there. X plus 3 goes that way. There you go. Then from 0, so that would be here. It goes e to the x, goes to about there. And both of those get the solid dots. That's essentially what e to the x looks like, at least in the range 0 to 1. And then x is greater than 1. If you plug 1 in here, you get 1, which is here. And then it goes down the way. Okay. If you can just ignore that line, which is freaking me out because it is distracting, it goes straight line, curve, straight line. Then you'll get a whole load of questions. Here's some. At x equals 1, right? Is this function left continuous, right continuous, or continuous? At x equals 1, what's this function?
Left continuous.
Okay, so you just focus on that, don't you? And do you see the left branch has got that nice solid dot on it? That's how you can tell a left continuous visually. Great. Okay, this is a bit messy because of my line, so I'll try and cover it up. There we go. That's a little bit better. At x equals 0, is this function left continuous or right continuous?
Right, continues?
Correct. If you look carefully, do you see the right-hand branch has a solid dot on it? It's all about where that solid dot is. That's the value of the function, by the way, as well. So if I said to you, what is the value of f of 1? Wouldn't you have to find out what e to the 1 is? And so the answer would be e, for example. Okay, let's see if we can find. Was that one a little bit, I don't know, easier to see left and right continuous? Okay. What have we got next? 18. Reversion of it. Now, although I'm doing this thing on paper, you know, you could just do it in Desmos and, you know, look at the picture. The only thing about Desmos is you have to know where the dots are, so that's something you have to be careful about. Okay, so there's a transition point at 1, 2, 3. Another transition point at 5. Right, so as long as you're less than or equal to 1, you're 3 to the power of x. So 3 to the power of 1 is 3. I'll make that 3. And then you go a half, 0, negative 1. So basically, it looks something like that. So that's what 3 to the power of x looks like, that piece. Now the middle branch is 4 minus x. It's going to be a circle at the one side, it's going to be a dot at the other side. And so if you go 4 minus 1, oh, 4 minus 1 happens to be 3, so it actually joins up with that guy. And it passes through here, and then it goes to here where it's a solid dot. So it would look something like that. Now, on the left-hand side, that's a circle, but isn't there a solid dot under it? So all that does is that they join together. It like meshes up the two pieces. And then it goes to square root of 5, and the square root of 5 looks like that. So now that I've got this guy kind of up and running, and here are some of the questions that they ask. They ask you for the value of the function at 1, and the answer to that is 3. They ask you for the value of the function at 5. Now, here you've got a choice, right? It could be that guy there, or it could be that guy there. I think it's pretty obviously here, isn't it? Because that's where the dot is. If you wanted to know what that number is, you could just say, plug 5 in here, and you would get the answer negative 1. Let's just talk about the rest of the questions. At x equals 5, left continuous, right continuous, or continuous? At x equals 5, which of those is it? Left,
Left
Right.
continuous?
you could be right, Vanessa, I just didn't catch it.
Oh, left continuous?
Correct. What's happening at x equals 1?
Me? Or
Anyone, you, if you want. What's happening at x equals 1?
continuous?
You see the difference between a continuous and a left and right continuous. Isn't a continuous, you go from one to the other and there's no gap. So if I was driving my little car, it's my kind of analogy, wouldn't I be totally safe? If I tried to drive my car, whoa, wouldn't I get killed? The road would just suddenly stop. So this is left continuous. This is continuous. Are we good? Okay, let me try a different approach. It's very visual, these. You really need the graphs in front of them, which is what was making my life a little bit tricky. So, here we go. Are you looking at question 2 graphs essentially here, right? Is that what you're saying? Not yet. Are you seeing it now? Okay, so I'm just going to use these graphs as if these were 2 different questions, right? So I can go through the process without getting too cluttered up with writing the thing down and so on. So let's focus on this left-hand side one. Okay. What's happening at x equals 5? Left, right, or continue, overall continuous? Left, right, or continuous? At x equals 5, what's happening here?
Left.
Left continuous. You see a solid dot. How about, well, let's use this one, right? This one here. What's happening at x equals 1?
Right.
What's happening at x equals -1? You're correct.
Continuous.
Okay. Look at this one now. What's happening at x equals -1? Right continuous. Yes, is it?
Right,
You're right.
continuous.
And at x equals 1, what's happening at x equals 1? On this one.
Continuous.
Continuous. Are you getting, it's very a visual thing, isn't it? It's pretty easy. Once you figure out what they look like, it's pretty easy to decide left continuous, right continuous, or continuous. Right? Okay, that's typically going to be your choices. I might be flogging a dead horse here. Am I flogging a dead horse here? Are you okay with left and right, or can I move on? You feel comfortable about me doing some different types of questions? Okay, so let's move on then and look at rational functions and what kind of continuity they can have. So this is basically my second one. Here are 2 different functions. Rational function is just another name for fraction function. Right? Actually, now I said that, there are 3 different types. That's a rational function. That's a rational function. And there's another example of a rational function. But each one of them has a different kind of shape, and each one has different features. Not all of these guys really look even vaguely similar to each other. Start with the first one. if you sketch in Desmos, this guy here, you're going to have to trust me on these things, but I think you can. Can you trust me? It looks like that. That's what it looks like. Would you agree that function has no problems? It's continuous everywhere. Agreed? There is no vertical asymptotes. There's nothing of a problem. So if somebody just threw a question at you and said, what is the overall limit as x tends to 2 of this function? Wouldn't you simply say it's 4 over 2 squared plus 1? The answer is 4/5. Wouldn't that be the overall limit? And there wouldn't be any problems. And if we said to you, you know, what have you got? You would say it's continuous everywhere. Great. So for rational functions, aren't they the nicest ones? Because nothing particularly horrible happens, right? Can't you find the value of the function at any point you like? Because it's continuous everywhere. So this one is continuous for every single value of x. And its domain from 141 is also every number, right? Can't you find this function for any value of x? The domain is usable values of x, places where you could get answers. So that's one of the 3 situations. And let's look at this fella. Also a rational function. And if you sketched it, it would look something like this. You might be surprised to realize that that is in fact a straight line. And it has a hole. And the hole is at x equals 1. Can you tell why, just looking at the formula, why there's a problem at x equals 1? Can you see it? At x equals 1, say again?
In the denominator, when you factor it out to equal 0, x will be equal to 1. And
yeah, and that's bad news, isn't it? Because 0 in the bottom is not good. So this is a rational function, right? It's made up of a fraction. But when you visualize it, when you graph it, it ends up being a straight line. But I can do versions of that where it's a curve with a hole in it. The main issue with this type of rational function is that they have what's called a removable discontinuity. You remember yesterday talking about the 3 kinds of, the 3 major types of discontinuity. There was a removable discontinuity. There was a jump discontinuity that you get with piecewise functions. And the third one was called an infinite discontinuity, right? A vertical asymptote. So in this case, this function is only continuous as long as it's not 1. And the way that you would write that down is negative infinity to 1 with a little curve bracket, union 1 to infinity. Okay. That is continuous for any value of x in that range, right? It's continuous here, right? It's okay here, it's okay here. It just has a problem there. Now, the domain of this rational function is its usable values of x. And it might not surprise you to realize that the domain is exactly the same as the places where the function is continuous. And that's not a coincidence. For rational functions, if you know the domain, you know where it's continuous, because the rational function is only continuous on its domain. In other words, any number on its domain is going to be continuous in that place. So you see these will be equal to each other. You notice that these are equal to each other, domain and where it's continuous, domain and where it's continuous. Now the third function, h of x, also a rational function, So it's 2x over x minus 3. And if I try and sketch this function, from 141, isn't this the most common type of fraction function that you get to sketch? Isn't there a problem at x equals 3? That problem is called a vertical asymptote. Okay. This particular function I happen to know has a horizontal asymptote as well. And if you sketch this function, what would it look like? For big fellas, it would look like this. And for values of x that are less than -3, it would look like this. There. Made a bit of a pig's wheel, but it looks like that. The key feature that this shape has got is that it has at least one vertical asymptote. Can you see it badly drawn as is? This is a vertical asymptote. In this function then, won't it not be continuous at x equals 3? We call that a vertical or an infinite discontinuity. So this function is continuous everywhere else except at x equals 3. And if you found the domain of this function, it would be the same. So here's a property, so again about fractions. The domain and the region where it's continuous are the same thing, right? The places where it has the domain exists, the function will be continuous there. So far, so good. Right. So it really depends on what kind of fraction function that you end up with, doesn't it? Whether or not you're going to have no problems at all, right? It's continuous everywhere. Whether it may have a problem, but it's removable discontinuity problem, or that it may have a problem, but it's a vertical and discontinuity. Now, some questions make your life a little bit more awkward. When you get this situation, they might actually say to you, how would you redefine f of 1 so that it wouldn't be discontinuous anymore? So what that would look like is you do a fraction, you do a kind of a piecewise function, and you would say, use that when x is not equal to 1, and when x equals 1, use a number. And what they're really asking you to find here is what that number there is. Because if you know what that number there is, can't you put it here and essentially plug up the hole? So removable is quite a good name. It means you can actually get rid of the discontinuity by finding out what it is. The problem is you have to know what that number is. I guess if you went to Desmos, couldn't you just read it off? But if you didn't, if it was an awkward number and you didn't really know how to do that, what you would do instead is find what the limit is. And whatever that number is, that's the red value over here. Okay, bringing up some stuff we've done a while back. Can you remember we tried to find limits of functions like this? And the technique we're going to use is factor and cancel.
The top factors as x plus 1, x minus 1.
And so we can now do the cancelling. And then you can just plug in the number and the answer we get is 2. So that guy is 2. And so when you get one of those questions, it says something like, maybe I could find the phrasing of it. Yeah, redefine f of 1 so that f is continuous at x equals 1, and thus the discontinuity is removed. Well, don't you just make f of 1 2? And now you filled the hole up. So when you have a removable discontinuity, which you will be able to see when you put it into Desmos, you sometimes are asked, okay, then how do I fill the hole up? That's what do I make f of 1 equal to? And you found out what it was by doing a little bit of algebra or being very careful in Desmos and clicking on it. Let me try that guy in Desmos and see if we can. I seem to remember it wasn't quite what I wanted it to be, but that's fine. So here we go. I'm going to put in the function y equals on the top. So I'll put a little bracket. X squared take away 1 divided by, put another bracket, x take away 1. There we go. Yeah, just what I thought. If I zoom in on, well, a little bit too much, can you see we basically got the straight line that I talked about? And this is x equals 1. And there, got it. Do you see it says 1 comma undefined? So I didn't do the little hole, right? But it did at least tell you it's undefined. But if you look really carefully to the left, can you see the number 2? Right, so that's what f of 1 needs to be. It needs to be equal to 2. If you do that, won't it fill the hole up and it's not undefined anymore? There we go. Any questions? I always get worried when I don't get questions, because it either means things are fine or you haven't a clue what we've been doing for the last 40 minutes and you don't know what to ask. So to make me feel happy, let me make the assumption that everything is fine then, right? So if you get a rational function, you'll feel comfortable that you know that's what's happening. So let me pick one. You know, an example of what I just did. As I said, most of these questions are going to be like removable discontinuities. So the one I'm choosing, oh darn it, where are you? This one, question 13. And the function is x squared take away 11x plus 30 over x minus 5. Now you would plug that into Desmos. Well, you can't see it, can you? Oops. Okay, that's the one I'm doing. So you would plug that into Desmos, right? And you're going to get a removable discontinuity. It's going to be a straight line with a hole in it, right? And can you tell me what value of x is going to have the hole in it? Agreed, 5. So all we need to do is kind of answer some of these questions. The one I'm going to do is figure out what the value of the function needs to be to plug the hole up, which is basically part B of this question. So part B of this question says, what does f of 5 need to be equal to make this function okay then and remove the discontinuity? So I'm going to do the overall limit as x tends to 5. And I'm going to do the factor and cancel method. You're going to factor x squared take away 11x plus 30, but isn't there a very big clue about how to factor the top because of what's on the bottom? Agreed? Don't you know the answer? It has to be x minus 5 times something, doesn't it? It just has to be. Well, if I know that one is x minus 5 and I know that number's plus 30, doesn't that make this have to be x minus 6? And if you do it, you see, hey, it matches, which isn't a surprise because it should have. So I can now cancel these two out and we would get the limit as x tends to 5 of essentially that, which is -1. So if I make the thing -1, won't I fill up the hole? Now, you could certainly do that the way we did the last one, right? Just click on the thing and it'll say it's undefined, then you read the height, and the height will be at -1, and everything's fine. But sometimes you're going to get a rational function. Let me make one up. Can you imagine you got a situation where that happened, right? Okay, and you would cancel. Well, this one, by the way, would be a problem at -3. Let's make that 8 then. I'll shoot in space. Let's make this guy -3, 10. That'll work. So you cancel these two guys out, and you go this fella, and you get 1 over x add 10, and you get 1/7. Well, see, that is an exact value. If you did this on WebAssign, you wouldn't be able to read off 1/7. Would you agree? All you get is, that's 0 and that's 1, and you're trying to guesstimate what that is. So do you see that sometimes you have to do it the algebraic way? Because if the value, the height, right, this thing here is not an easy number, right? If it's 4, Desmos is great, right? If it's -2, Desmos is great. But if it's 3/11 or 1/7, can you see that Desmos isn't going to get you out of the hole, right? You won't be able to do that kind of accuracy.
And on a midterm, you would want us to do this as well, so you could see our work, right?
Exactly. And for partial credit reasons, right, I want to see what you did to get that answer. So even if you did it wrong, you would still get points because you were doing it the right way. Are we cool down fractions, removable discontinuities if they have any, and how you fill the hole up? Of course, if they don't have any, isn't the question going to be really quick? Continuous everywhere, not much else you can ask after that. And if it's got a vertical asymptote, well, couldn't you ask things like, where are the vertical asymptotes? X = 2, X =